In this work, we introduce a generative framework for synthesizing high-level character behaviors, allowing users to automatically populate virtual worlds. State-of-the-art crowd simulation models mainly focus on low-level tasks like collision avoidance and basic navigation behaviors, such as steering, path following, and flocking. However, creating compelling crowd scenes demands more than just functional movement. It requires capturing high-level interactions between agents, their environment, and each other over time. We present GenC, a generative framework to automate the task of authoring high-level character behaviors from simple text descriptions. GenC takes as input a text prompt from a user and automatically generates an environment plan and a crowd scenario graph capturing interactions between agents and the environment. GenC allows us to automatically populate diverse virtual environments with the simulated characters exhibiting varied and dynamic behaviors. For instance, here, for the given prompt, we mainly observe students discussing over lunch, chatting under a tree, while others are waiting to get their food. Secondary behaviors relevant to the context can still be observed in the scene, such as checking the announcement board or wandering around the campus area. Our generative framework consists of three main components: synthetic data generation using large language models, learning, and crowd scenario generation. We collect synthetic crowd data using two sequential LLM queries. The first focuses on generating the environment, and the second on authoring crowd events. We use a structured JSON representation for both query responses. Then, we represent each scenario as a crowd scenario graph, encoding the sequence of actions and interactions of each agent. We train a generative model to synthesize novel crowd scenario graphs, mainly conditioned on a textual description. Our model combines a dual variational graph autoencoder architecture with a condition net acting as a prior network to jointly learn a structure latent space and a features latent space. During inference, we sample from the learned prior distribution to generate novel crowd scenarios guided by a user-defined text prompt. These crowd scenarios can be applied to different environment plans, custom or LLM generated, to synthesize diverse simulations. Next, we show additional results obtained with GenC. Here, we present results for a given prompt used to populate a train station scene. We observe travelers waiting for their trains and conversing, while others queue to buy coffee. Additionally, secondary behaviors emerge, such as travelers lining up at the information desk, people using the vending machine, and others heading toward the train platform. We present close-ups from different runs using the previous textual input description. Given a trained model, GenC produces diverse outputs from different input text, rather than being limited to a fixed set. Please refer to the paper for additional analysis. Here, we show that given a similar virtual environment, we can generate two distinct scenarios. On the left, we see travelers mainly waiting for food and talking to each other. On the other hand, on the right, travelers check the schedule board and ask for information at the main desk. Here, we follow two students during their lunch break on campus. First, they visit the food truck. Then, they meet up with another friend and all head toward the food counter. Finally, they walk over to a table, get their lunch, and chat with others. Additionally, we follow two friends as they navigate through a train station. First, they pause to ask for information about their journey. Next, they approach the ticket counter to purchase their train tickets. Afterward, they check the schedule board to confirm their train details. Finally, they wait in the seating area, chatting as they pass the time until their train arrives. By leveraging a generative model, our approach generalizes across varying environments and numbers of agents, enabling characters to consistently exhibit diverse behaviors at different scales. In contrast, directly using an LLM often results in repetitive actions, higher cost, and invalid simulations. Please refer to the paper for further discussion and analysis. Thank you for your attention.